I interviewed, Professor Whiteman was one of the first people I talked to about surface science here. And he told me something, his reason for loving surface science, and I'll never forget it. He said, John, one of the most wonderful things about surface science is that everywhere you look, there's a surface. And that's really true, right? And every one of those surfaces, there's chemistry going on. What interests me is what happens when gas phase molecules collide with surfaces. So if you look around this room, you see surfaces. Every one of those surfaces is being bombarded by gas phase molecules. I'm really curious about what happens to those gas phase molecules. Do they just bounce off? Do they come to rest on the surface or diffuse into the material? Of course, material. If they diffuse in, do they break apart into other things? What is the fate of gas phase molecules? And then once they're on the surface, are they released back into the gas phase later on? That's what my research program does. Try to understand the fate of gas phase molecules and apply to surfaces. I've got a wonderful group of students who are mainly located, so you all recognize this picture. My research, this is an older picture now. That looks very different, that's why you're all here. So, when I first started here in 1999, many of you will remember there were labs, old labs in Davidson. I taught analytical chemistry here, non-air conditioned labs in Davidson. Right now, and my lab was originally here in this back wing of Davidson. We've moved and we're in the basement of Pond Hall. So if you're walking around today on tours and want to see some of our equipment, it's in the basement there at Pond Hall. And that is where we do our surface science. These wonderful people. By we, I mean graduate students like this. Some of you may recognize their faces. I'm happy to answer questions on any one of them and let you know where we are right now. Some of them are still here at graduate school. Some of them are off doing other wonderful things with surface science. Here's an older picture. Some of you may recognize colleagues, former graduate students. This was taken maybe 10 years ago, maybe 12 years ago or so. This is a more updated picture of one of the instruments next to my research lab, and I bring this up in particular because when many of you were here, this was a surface analysis lab headed up by Frank Cromer. It's not still a surface analysis lab, but headed up now by Xu Feng. He's right here, and he's teaching a class of inorganic students, actually. This is Professor Amanda Morris's class of students. And what they're doing is learning how to use this instrument here, which is the state-of-the-art X-ray photoelectron spectrometer. It's replaced most of Frank Cromer's work now. And this is one of the three best at the time. It's been here about a year. One of the three best X-ray photoelectron spectrometers ever installed at a university. So we're very proud of it. And what it does is it gives us an elemental analysis of the surface. It allows us to see what elements are there. So if a gas phase molecule sticks to that surface, we want to know what elements are involved. We use this spectrometer. I'll give you a very brief overview of some of the research in my lab. We study, everywhere you can think of a surface being involved. Nanoparticles are a really fascinating system of surfaces where they can encourage certain reactions together. They can catalyze particular reactions. I have a group of students studying things like photocatalytic propene epoxidation. Propene is a really important precursor for a lot of polymers. This fits in really nicely here with the polymer programs. We're studying how to make propene, how to convert propene into propene oxide. We're studying the oxidation of toxic compounds through experiments done here and a theoretical chemist named Matt Muir from the University of Minnesota. One of the richest areas of research in my group recently, which I'm very excited about, is the destruction of chemical warfare agents on surfaces. And we're using things called metal organic frameworks. My good colleague Amanda Morris is a collaborator on this project. We'll tell you about metal organic. By the way, Professor Amanda Morris has no relation to me, but a really cool last name. We have papers now where those last two authors are Morris, which I think is about the best author list possible. That work is actually supported by theory. Diego Troy and Morris are both at Virginia Tech. I'll tell you just a little bit about that in the next few slides. Beyond chemical warfare agents, we're interested in atmospheric chemistry. So a tremendous amount of atmospheric chemistry. You think of atmospheric chemistry mainly being gas phase molecules, but there are a lot of surfaces in the atmosphere. that you actually don't see. Even in this room, there are about 100,000 tiny aerosol particles per square centimeter. So, a little square centimeter kind of scares you to take a deep breath, right? So these are micron-sized aerosol particles. They're mostly water with organic compounds on the surface of those particles as well. And a lot of other molecules that react on the surface of those tiny aerosols. A lot of atmospheric chemistry involves surface chemistry on those aerosols. My graduate students working on that project. And then a brand new project. So one of the things I love about Virginia Tech is researchers are open to collaborations that cut across departments and disciplines in a very big way. One way that my research group has benefited from, and I've become very excited about this project, is that I was contacted about 9 months ago or so by Rohan Yu, who's a professor in mining engineering. I never thought I'd be working with someone in mining engineering. But he tells me that there's a national security problem right now, and that is that we get most of our rare earth elements from China, and we totally rely on them for rare earth elements. Why is that important? Because rare earth elements are in every single device you own, electronic device, from your cell phone to your computer. And they're running out in China, so we desperately need a new source of rare earth elements. It turns out there's plenty of rare earth elements in our backyard. In the Hokie Stone, there are rare earth elements. Believe it or not. The problem is it's really difficult and very expensive to extract them from the Hokie Stone, limestone, and the coal. Mainly the things left behind that no one wants after you extract the coal. But it'd be wonderful if we could use that material. There's a lot of rare earths there. So we're working with him to try to extract rare earth elements from the mountains of Southwest Virginia. I don't want to take too much longer. My colleagues who I know want to speak, but maybe I'll end here and just give a brief introduction about our collaboration. If you don't know anything about chemical warfare agents, this is what they look like. So this is my only slide with compounds on it. I put this up just because, just to show you, these are the most toxic compounds ever synthesized. Right? The most toxic, unclassified, I should say. There are other compounds that have been synthesized, but these guys are really bad. And the thing to notice about them is they're really small. Right? These are not these enormous biomolecules. These are tiny things, organophosphates and organophosphonates that are frighteningly simple to synthesize. What we do in my group is try to develop a material, surfaces, catalysts to actively decompose these before they become a threat. So we want to use our catalysts in filtration for buildings, for gas masks, for soldiers. And we're now embedding materials called metal frameworks that Professor Morris will tell you more about into materials like clothing to actively decompose chemical warfare. And this is supported through a large collaboration. So I run a center now through Virginia Tech that brings together researchers at Virginia Tech, both Professor Morris and Professor Troya, who will get to speak here later. Emory University, Brookhaven National Lab is where a lot of our research is conducted. Kennesaw State University, Stony Brook University, and finally Edgewood Chemical Biological Center. At Edgewood Chemical and Biological Center, we can actually do experiments, catalysis with real chemical warfare agents that I can't do here at Virginia Tech. And this is an ongoing collaboration that you can learn more about if you go to multi-rad. VT.edu stands for Multidisciplinary Research for Agent Destruction. I think that's a good place to stop. I'll be happy to answer any